continue. Do you have any question regarding exercise 1, where we looked at rounding error and truncation error? If not, we can move on, and next topic will be on stability condition for the Runge-Kutta method. For ordinary differential equations. So we consider the third order TVD Runge-Kutta method. Third order total variation diminishing. Runge-Kutta method. That is the one that we had in chapter 8, 6. That was on the Burgers equation. But we use it here now for y prime equal to f of y. So the name is an autonomous ODE. So we have no time dependence here. And the method is the following. If we write it in the ODE notation, then in the first stage, which we denote by a superscript 1 in parentheses, we take the value at the old time level plus delta t times the right-hand side of the ODE at the old time level. So as you see here, this is just a simple explicit Euler step. So that's the result of the first stage. Then the second stage, y superscript 2 in parentheses, is equal to 3/4 of the approximation at the old time level plus 1/4 times the value that we get from the first stage plus 1/4 times the time step times the right hand side evaluated now with the first stage. And then we get the solution at the next time level by taking 1/3 of the approximation at the old time level plus 2/3 of the second stage value plus 2/3 times the delta t times the ODE right hand side evaluated with the second stage value at y2. So that is the third order TVD Runge-Kutta method. So that we know as number 1. And so this method can be shown to have the amplification factors. That is, when you apply this method to the test equation. So third order TVD Runge-Kutta method applied to the test equation. The test equation, that is then the one y prime is equal to lambda y. Lambda is complex and it is constant. And we assume, which is not important, that the initial condition is 1. So you could simply do just one step with that. So the solution at y1, that would give us then the amplification factor. So that yields then actually then the amplification factor. We don't do it because it's just straightforward to put in this for f of y lambda y. So here everywhere lambda yn, lambda y1, lambda y2, and so on. Just put in the stuff. And what we get in the end would be the following. Let's see, would be 2g of lambda delta t. We would get the sum L from 0 to 3, and we would get lambda delta t to the power L divided by L faculty. So we get an approximation, essentially, of e to the lambda delta t, up to including the third order terms. And so that we have, and from that we get the stability domain. Say stability domain is then the following. That is the set of all, so I denote it, I write it in this form, TDD RK3. So the stability domain of this method is then the set of complex numbers for which the absolute value of the amplification factor, here we put in, instead of z, put for z, we put for lambda delta t, we put z. So we start from 0, go to 3, and then we have here z to the power L divided by L faculty. That has to be smaller or equal to 1. That is the condition. And it turns out that we get the following. This is the real part. Now I convert again to go to lambda delta t, the imaginary part of lambda delta t. And we get something of the following kind. It's similar to the stability domain of the classical Runge-Kutta method, but not quite. So it should be symmetric, of course. Here it does not look like, but it should be symmetric. Also in this it should be symmetric. So here we have the origin. Here we have, turns out, this value is square root of 3 times imaginary unit. This value here is minus square root of 3 times the imaginary unit. And this bound here is minus 2.51. Let's see. It's not important, all the digits, but I have them. So let's see, where do I have it? There it is. 2.7. It is just there. There are still more digits, but it's a little bit larger, a little bit lower than minus 2.5. So in this stability domain, that is then this here. So interesting for us is when lambda is real, then lambda delta t must be in this region here to be stable. Then it is inside the stability domain. And then this amplification factor then is smaller or equal than 1. Then we can get a stable solution with this method. If lambda is imaginary, purely imaginary, then lambda delta t must be within this region here. Then it is stable. If it's outside, then the amplification factor will be larger than 1, and that will be amplified in each time step, and then that will quickly go beyond all bounds. So then we have an instability. So that is something that we know, or that we can derive that. So actually this is, you can do this here, to derive these bounds fairly easily by assuming that the lambda is, or that if we take this here, that it is purely imaginary. Then we can derive, find out that. Here we can find out it must be smaller than 0 when lambda is real. This bound we have to have a, to find the root of the polynomial, this third order polynomial, but that can also be done. But we skip that. The task is instead the following. So now it is just the preliminary things. So the task is now, the first task is determine the stability condition of the third relativity Runge-Kutta method applied to the following ODE. That is similar to the one that we had in exercise 3, I think. That is in orientation now number 3. That is y prime is equal to minus 100y plus 200. And some initial condition, y of 0 is equal to 3 in this example. So that is task A. Task B is determine the stability condition of relativity Runge-Kutta method 1 applied to the following ODE, which is a bit unusual, but you will, I think, remember, or it's not completely unknown to us. It is the following. We have here the Fourier modes, u hat k. Time derivative of that is equal to minus imaginary unit, minus I, the advection velocity c divided by the grid spacing delta x times the sine of the wave number k times the grid spacing times the Fourier mode u hat k. With some initial condition. It's not so important. If we would do it, we would have a discrete Fourier transform of the initial condition. So that's the initial condition at a grid point xj. Minus I k xj. Discrete Fourier transform of initial condition of u of x0 is 0. And this expression of this ODE is arising when we do Fourier analysis of the semi-discrete method to discretize the linear advection equation. So the ODE is arising from Neumann stability analysis of the semi-discrete equation see, that would be number 5 duj dt is equal minus initial velocity divided by 2 delta x times uj plus 1 minus uj minus 1 of the linear affection equation. Which is ut plus c ux equal to 0. So c is our affection velocity. So that means we discretize that by a central difference approximation in space. And if we know, if we apply to that the explicit Euler method, then this is unstable. But using this Runge-Kutta method, or any other Runge-Kutta method that has something on the stability domain of the imaginary axis, we can get the method stable. But here for the application, it is simply to first to look at this scalar ODE for that we had also a similar one in exercise 3, and then to look for this ODE that is arising when we insert a Fourier mode in here. So we insert here for uj a Fourier mode, uk e to the I kxj, we get this equation. So, but the task is just only to derive the stability conditions for this ODE and for this ODE. That's the task. So then we do that. So solution A. We have our right-hand side of our ODE. We can write them in this form. It's minus 100y plus 200. That is our right-hand side of the ODE. That is the way we usually write an ODE. And the connection to the test equation is by the Jacobian of the f with respect to y. That is then the lambda in the test equation is given to us by the partial derivative of f of ty with respect to y. If this would be nonlinear, then we would have to linearize it. But in our case, it is no problem. We can get that directly. So this is minus 100. So that is just, in our case, we have a linear ODE, so that's no problem. So then we can, from that, knowing that now our lambda in the test equation is real, then lambda delta t has to be in the interval for of the stability domain. Now lambda that is real, so it has to be on the real axis. So lambda delta t has to be in here. That will be the condition for getting stability. So we can write that. So our TBD Runge-Kutta method 1 is stable for the ODE that we did labeled number 3 if then the condition is, let's see, here, if the following condition is satisfied, if the lambda delta t, which is in our case the minus 100 delta t, is inside this interval. Because lambda is now real, and to be inside the stability domain, it must be in this interval. And the interval is then according to what we said. We have not derived, but I told you how to do it. It is this number, and the right boundary is 0. So it has to be smaller than 0, which is the case, but the bound is then that it has to be fit in here. And that is then using this stability condition. And that is then satisfied if minus 2.5127 is smaller equal than minus 100 delta t smaller equal than 0. So that is what this means. So this inequality here, that is okay, because we assume that we have a positive time step, so that is then no problem. But this condition will be then the condition that limits our time step. So from that we get this condition here, that is then, let's see, that will be then okay for delta t smaller equal than this number, 2.5127 divided by 100. So that means our bound is simply 0.025127, so it's a small time step. So that is then what we get. So stability condition is then stability condition of the Runge-Kutta method of 1 for the OD that I just removed is then that delta t has to be smaller equal than 0.025127. So that is the result. So here we had lambda real, and then we had to look on the real axis. That lambda delta t has to be inside this region here. And that we get the condition. Now this one here, which makes a link to PDE discretization. And we have come, as I told you before, to this by inserting the Fourier mode into our central space discretization of the linear affection equation. But what we get here is then this equation, this ODE, for the Fourier mode, U hat k. And in there we have a lambda, and the lambda is this here. And that is then imaginary, it's purely imaginary. So then we shall use that now. So the solution to D, that is our ODE4, corresponds to the test equation y prime lambda y with the lambda that I just circled is equal to minus the imaginary unit times the advection velocity delta c divided by the grid spacing times the sign. Now I use theta here for the wave number k times the grid spacing. And we note that lambda is purely imaginary. So, and from that we can then conclude that lambda delta t must be in this interval here. Because if it's purely imaginary, then it must be on this line here to be stable. So then the Runge-Kutta method is stable for this ODE4 if the lambda delta t is equal to minus I. Now we multiply this by delta t, we take it in here, delta t divided by delta x sine of beta, if that is inside the stability domain, and that will be in this case from minus to plus square root of 3 times I. So that will be the interval that is relevant to us. Minus square root of 3 plus square root of 3 times the imaginary unit. So we are, that is indicating that we are here. And that is satisfied for the absolute value of lambda delta t that has then to be smaller equal than square root of 3. So that is another way to express this. And here we use now following. As you see here, that is very well known to us. That is the Courant number. So that is the capital C, which is the Courant number. So that means when we look now at the absolute value of this, absolute value of minus I is 1, then we will have here the absolute value of the Courant number times the absolute value of the sine of beta, and that has to be smaller equal than square root of 3, which is approximately 1.732. So that will be then our stability condition. But we are not yet fully ready for that, because the trick that we do, that we usually play here, is that we say, if we have in here, if we make this estimate, that is true, the sine of beta absolute value is always smaller equal than 1, so we can get, then this will be our stability condition. So if the absolute value of the Courant number is smaller equal to square root of 3, then this is satisfied, and then we are in the stability domain. So that is the idea. So then we just write that. So then satisfied for, so from that we get then the stability condition. Runge-Kutta method for this equation 4 is then, well, it turns out that all what we have then is this here. So we have here that the absolute value of the Courant number has to be smaller equal than 3. Which is approximately 1.732. And remember, the Courant number was C delta t divided by delta x. So that is our Courant number. So that is the stability condition. So that means when we apply the Runge-Kutta method to solve our linear advection equation with a central difference, it works. It will be stable, and we can get up to Courant number of this. That is very much unlike for the explicit Euler method. Explicit Euler method, you saw that is unstable, but this method is stable, and it is thanks to the fact that we have the stability domain is containing some part of the imaginary axis. The stability domain of the explicit Runge-Kutta, of the explicit Euler method, only has a circle here. It has only the 0, nothing more on the imaginary axis. So that is unstable. So we are immediately outside with that. We are immediately outside the stability region of the explicit Euler method. But for the Runge-Kutta method, we have a stable region. So then it is possible to use this method to solve the linear advection equation with central differences. Okay, So that was an example making actually a link from the ODE methods to PDE discretization by the Fourier analysis. Because the Fourier analysis led to this ODE method for the Fourier modes. And then we can apply our techniques, here the stability of ODE methods, to this. So now we come to the final exercise of today, and that is related to the convergence of the finite difference method for the heat equation. We have been looking a lot at the forward time-centered space method. Now we want to look at a different method. And that is the Crank-Nicolson method. Convergence of Crank-Nicolson method for the equation. So the task is show that the Crank-Nicolson method for the heat equation, that Crank-Nicolson method for the heat equation, which is ut time derivative of u is equal to the thermal conductivity times the second derivative of u with respect to x. So u is now our temperature, and the discretization is the following. We have the usual way to discretize the time derivative at grid point xj by taking the value at the new minus the old time level and divided by delta t. And then the trick with the Crank-Nicolson is that we essentially have an average of explicit and implicit Euler. So we take then the factor 2, that is doing the averaging, I take that here in the denominator, together with the delta x squared. And then we have the second derivative approximation at the old time level n, which is the usual way. And so that is the old time level, and a similar approximation then at the new time level. Uj plus 1 n plus 1 minus 2 uj n plus 1 plus uj minus 1 n plus 1. So this is at the old time level, and this is at the new time level. And to get it right, we have done here then the averaging, so definitely the 2. So we are supposed to show that this method is convergent for any Neumann number, or that we call R, and the R is the ratio of the thermal conductivity alpha times the time step divided by the delta x squared. So for any of these greater or equal to 0. And we should also show that the method is second order accurate in space and time. Second order accurate in space or in time and space, doesn't matter. Let's see. There is an additional question. The additional question is whether you recommend this method to be used for a steady state computation. That question here. Do you recommend to use the Crank-Nicholson method with plus f of xj here on the right hand side on RHS, that is the right hand side, of equation 1 to compute the steady state. So that's a source term, you can imagine that. To compute steady state of the heat equation with a source term. By using this method, using a very large time step. This is the question that we should. Okay, and the hint is that we can show accuracy by considering time and space separately. So that would be a hint. So then. Finish today, but we can start with the consistency. So the solution then will consist of 3 steps. So the task is we should show convergence. What do we need to show? We remember Lax equivalence theorem. Lax equivalence theorem says if we have a consistent finite difference method for a linear initial value problem, then stability and convergence are equivalent. So that means we have to show that this Crank-Nicholson method is consistent so that we can apply the Lax equivalence theorem, and then we show that it is stable. If we have shown that it is stable, we have shown that it is convergent. So that is the idea. So first consistency, then stability, and then we use Lax equivalence theorem to draw the conclusion that it is convergent. So these are the 3 steps. So first step, consistency. Well, I would have written a hint, I just said it orally. So we consider the method of lines. And that is, we consider then that we do a discretization first only in space. Then we get also what we had already in the previous example for the linear advection equation. We get the time derivative is still continuous, but the space derivative is then discrete. So then we get this discretization here in the usual way. So, and then we can look for the truncation error first of that. So then we take, here we focus then on the truncation error of the space discretization. So the truncation error then is, in that case, if we take then the d of u of x, we go to xj through x dt minus, take that on the other side, alpha delta x squared. And then we have here the u, the exact, we've put in now the exact solution, u of xj plus 1t minus 2u of x, I need the j at the moment here, t and plus u of xj minus 1t. Okay, so then we have to compute this. And then we get the spatial, the truncation error for the spatial discretization. And that is then Taylor expansion in the away. That. So I give this here a number. 3. So we use Taylor expansion. Around x equal xj. And we skip below xt below this simply. We don't write it, but we imagine that everything is the function and its the derivative is at x and t. So then we put it directly in. We know, I think by now we are quite comfortable with that. So the first is the time derivative. There we don't need to do anything. That is already given to us. It's still analytic. Then we have alpha delta x squared. And now we have the u of x plus delta x. So the u plus delta x ux plus delta x squared half uxx. So here we can now do all our nice Taylor expansion. And we do it here actually quite a bit because we want to have, let's see if we need that at the end. Let's see, yeah, we need the next one. We need the next one, that is delta x to the power 4, 24 uxxx plus order, we stop here, to the power 5. And then we have taken into account this one. Then we have minus 2u and then plus u of x minus delta x. So then we have the minus 2u and then the plus u minus delta x ux. So then we have just to write things properly here. Minus delta x to the power 3, 6 uxx and plus delta x to the power 4, 24 times the fourth derivative plus order delta x to the power 5 and the whole bracket. And then we see most thing cancels, and we can simplify that quite a lot. And the result is following, that we get from this that the truncation error is equal to, so first let's look at the u's here, they cancel, u minus 2u and u, the plus, the ux, delta x ux, the minus cancel, and also this one cancels, so we get just this term, that is we get ut minus alpha uxx. So they survive, and the delta x squared by this cancels, so we get that. And here we get this twice, and the delta x squared is then cancelled, so we get then here the delta x to the power 2 divided by 12, and the fourth derivative. If we would go further, this would have a plus and this would have a minus. So the fifth order would cancel, and the next one would be the sixth order, divided by the delta x squared would be fourth order. So we would continue, I just didn't write it, but if we would do it, we would get this one here. But the catch is now that we can use that we have inserted the exact solution in here that fulfills the ODE. So that means ut minus alpha uxx is 0. So we get then that we get minus alpha delta x squared divided by 12, fourth derivative plus order delta x squared. So that means this method is second order in space. So then we are concentrating on that. So it is second order accurate in space. Okay. So we stop here and continue then tomorrow by then showing that the trapezoidal method that we use in time is second order in time. It is easier to do it that way. We could also do it directly, but this gives Taylor expansions which are a little bit unpleasant. You can do it, but I think it's easier to do it first in space and then in time. And then we do some other exercises, and I want also to show you tomorrow a demo from videos from Star CCM Plus. That's a commercial tool that is used in industry or also in academia. Okay, so we stop here.